All right, welcome back to the deep dive. So for this one, we are focusing on an opponent you literally cannot see.
Uh-huh. The silent one.
The threat that works relentlessly on a molecular level. We're talking about ultraviolet radiation.
Right. And our mission today is to figure out how scientists are building these tiny personal guardians you can actually wear.
Guardians that can warn you about this invisible danger. It's fascinating stuff.
It's all about control, really. I mean, for so long, we've just relied on these, general guesses.
Like the UV index on your weather app.
Exactly. Or just setting a timer to reapply sunscreen. The research here is aiming for something way more personal.
It's about how much damaging light you specifically have absorbed today, based on your own biology.
Your own skin.
So let's set the scene. Imagine you're on a beautiful day hike, maybe just working in the yard.
Yeah.
That sun feels incredible, it's warm, it's restorative. You put on some SPF 30, but deep down, sunscreen isn't perfect.
You always miss a spot. Or you sweat it off.
Right, and the immediate burn you feel, that redness, that's usually UVB, but that's not actually the real enemy we're talking about here.
Exactly. That's what people focus on, the quick, painful sunburn from UVB. But when you look at the stats, it's pretty staggering.
What are we talking?
95% of the UV radiation that actually reaches the Earth's surface is UVA.
95%.
Yeah, that's the longer wavelength stuff. It runs from about 315 to 400 nanometers.
And what makes UVA the stealth bomber of the solar spectrum?
It's the wavelength. It lets it penetrate deep, deep into the dermis, the inner layers of your skin.
So it's not just a surface burn.
Not at all. It's causing this cumulative long-term damage that leads to photoaging, and this is the critical part, it increases your risk of cancer over time. You never feel it happening in the moment.
So the stakes are real. Medically, we need something better than just guessing.
We absolutely do. We need to prevent you from reaching what's called the minimal erythema dose, the MED.
The MED. Okay, what is that?
Think of it like your personal biological tipping point. It's the exact amount of UV radiation that causes specific, detectable damage to your skin.
So my MED would be different from yours.
Totally. If you have fair skin, your MED is reached way faster than someone with naturally darker pigmentation.
So a wearable sensor that tracks your accumulated UVA and just pings you, saying, hey, you're at 90% of your personal limit, that would be a game changer.
A complete game changer for long-term health monitoring.
Okay, so let's unpack why this is so hard. Why couldn't scientists just, take the super accurate light sensors from a lab and shrink them down?
Yeah, why not just stick one on your arm?
Right. Why is this such a research challenge?
The villain here is material mismatch. Plain and simple.
Material mismatch.
Those traditional UV detectors, the really good ones, are made of things like gallium nitride or zinc oxide. They're rigid and they're opaque. They're built for a lab bench, not for your body.
So if a wearable is like a high-tech suit of armor that moves with you, using those old sensors is like trying to build that armor out of glass plates.
That is the perfect analogy. The second you bend your elbow, the whole thing just shatters.
Wow.
I mean, your skin stretches a ridiculous amount. We're talking 200, sometimes 300% strain.
So when they first tried to put these rigid materials on flexible surfaces, it was a disaster.
A total disaster. And it wasn't just that they broke physically. They had these crippling electronic flaws, too.
Okay, what were those?
Well, 3 things killed the early attempts right away. First was something called high persistent photocurrent.
A ghost signal.
Basically, yeah. The sensor kept saying it was detecting light, generating a current, even after the light was gone. You get constant false positives.
So you could step into a dark room and your sensor would still be screaming that you're getting blasted by the sun.
Precisely. The second major flaw was poor discrimination. It couldn't tell the difference between dangerous UV light and, harmless visible light.
Which is kind of the whole point.
Kind of the whole point, yeah. And the third, which is just ironic, was instability. Exposure to actual sunlight broke down the sensor itself.
That structural problem is so interesting because you can't just make the material, like gallium nitride, stretchy. You have to change the shape.
Yes. The scientists solved the mechanical problem not with chemistry, but with architecture, with geometry.
They started using things like flexible gold films with microcracks or these Serpentine and Kirigami designs.
Kirigami, wait, like the Japanese art of cutting paper? How does that even relate to microelectronics?
It's structural genius. Think of a serpentine design like a tiny, super thin S-curve, like a spring.
Okay.
When your skin stretches, the material itself doesn't have to stretch. The S-curve just straightens out a bit, absorbing all that strain.
Ah, I see. And Kirigami.
Kirigami takes it a step further. They make these strategic cuts in the material, so when you pull on it, the whole structure expands, kind of like an accordion. The shape protects the delicate electronics inside.
That is so clever.
Okay, so that fixes the breaking problem. But you still have the electronic mess, the ghost signals, the poor discrimination. And that brings us to the core of the research quest here. Two totally different solutions to the same problem. Let's start with the high-tech one.
The team in South Korea, led by Song-Jung Kang.
Yeah, their idea was, instead of one perfect material, they decided to build a stack.
They called it a multi-junction heterostructure. It sounds complicated, but your analogy from the source was perfect. It's like an electronic lasagna.
An electronic lasagna.
Yeah.
Where every single layer has a very specific job. So what were the ingredients in this lasagna?
And they chose 4 specific oxide semiconductors. And the key here is that these materials have what's called a wide band gap.
Okay, a band gap, in plain English.
Think of it like an energy wall. If the wall is really high, low energy light like the visible light you see with, can't get over it, just passes right through.
Which means the sensor is transparent.
Exactly. But the higher energy UV light can clear that wall. And that's what triggers the sensor. It solved the discrimination problem right off the bat.
That's brilliant. So what were the specific materials?
They use zinc and tin oxide as N-type semiconductors, which means they donate electrons.
Okay.
And then cobalt and hafnium oxide as P-type, meaning they accept electrons, creating these positively charged holes.
So you're stacking these positive and negative layers, creating these junctions. You're building an optimized highway system for electricity.
That's a great way to put it. The PN junctions, those are the workhorses. When UVA light hits, they create the signal by separating the electrons and holes. But the real genius, the thing that fixed the go signal, was the NN and PP junctions.
Like express lanes.
They are the express lanes. But more than that, they create this internal electric field that just sweeps away any leftover charge. It cleans up the signal incredibly fast.
So no more ghost signal.
Gone. That optimized highway system got rid of the persistent photocurrent that just plagued all the old tech.
And the result was a sensor that was over 80% transparent, and it was super stable. That's the high-tech, data logging, super precise solution.
Right.
Now let's do a hard pivot to the low-tech Maverick.
The Haptics device from Carnegie Mellon and UC. This thing it's just a completely different school of thought.
It is brilliant in its simplicity. We're talking about a small, low-cost wearable bandage or a sticker.
With 0 digital sensors. 0 microcontrollers.
No way. Seriously, if there's no battery and no computer chip, how does it know when to alert you?
Pure physics. It's an energy harvester.
So think of it like a solar piggy bank.
A solar piggy bank is perfect.
Yeah.
A little solar cell on the bandage collects the ambient sunlight, and it stores that energy in a tiny capacitor.
And the amount of energy collected is the measure of your exposure.
It is the measure.
Yeah.
There's a little knob you can set beforehand to set your limit. And when that piggy bank is full,
The buzzes.
it releases the stored power through a tiny haptic actuator, the little vibration motor. The alert is felt directly on your skin. You don't look at a screen, you don't sync an app, you just feel it.
Okay, that sounds amazing for accessibility.
Yeah.
But let me push back on this a little.
Go for it.
The high-tech stack gives me data logging, it's super precise, it connects to an app that's calibrated for my skin type. The Haptics device just buzzes. Isn't a lot-only system really that useful?
That is the crucial trade-off, right? Precision versus accessibility.
Mm.
The Haptics device is definitely less precise, but it's cheap, it's disposable, it's maintenance-free, it requires 0 user engagement besides just feeling the buzz.
So for, like, global health monitoring or for kids at summer camp, it's perfect.
Invaluable. And it's so effective because it moves that critical information off your overloaded eyes and ears and puts it straight onto your sense of touch.
So we have these two paths sort of converging on a solution. What happened when they took that high-tech sensor and got it ready for prime time?
They did it. They successfully integrated the semiconductor stack with a Bluetooth circuit and a smartphone app.
So they achieved the ultimate goal.
They did. Real-time tracking of UVA and the ability to issue skin-type-specific warning alerts. It pushes these oxide semiconductors way beyond just being in displays into, genuinely personalized health monitoring.
And this innovation isn't happening in a vacuum. It's part of this huge wave of wearables all built on that same flexible material science.
Absolutely. Just look at smart rings like the Oura Ring or the Ultrahuman.
Yeah, they're everywhere now.
They monitor heart rate, sleep, temperature, all with incredible accuracy And they're comfortable because they use those same Serpentine and Kirigami architectures we talked about.
Right.
They can handle that 300% strain without breaking.
And it's not just jewelry. The whole smart fabrics market, where the sensors are woven right into your clothes,
Oh, yeah.
that's forecast to hit nearly $90 billion in the next decade. All of this, the transparency, the flexibility, it's the foundation for that future.
And if we go back to why that simple vibrating alert is so effective, there's some really cool research on safety warnings. They looked at these haptic vests for, say, construction workers. Vests that vibrate to warn them about an approaching danger.
Okay.
And they found something fascinating. Location-based alerts, just knowing when or where the danger is, were way more effective than some complicated pattern of buzzes.
That makes so much sense. If you're chasing your kids around a sunny park, you don't want to stop and try to decode a complex vibration on your wrist.
You don't have time for that.
You just want a clear, immediate message, danger zone reached. Get inside.
Exactly. The human factor studies showed that short, sharp vibrations create a higher sense of urgency. So whether the alert is from a super precise Bluetooth device or a simple solar-powered bandage, the tactile signal is the best way to cut through the noise.
So we started with this invisible threat, UVA light, which penetrates deep and causes this unseen long-term damage. And now, thanks to the structural genius of Kirigami and the electronic lasagna stack, we have sensors that are transparent, they're flexible.
And they communicate directly with our skin, adapting to our individual biology.
The age of just guessing based on the UV index, that's ending.
The age of personalized environmental awareness is just beginning.
So here's a final thought for you to chew on. If we can now build these transparent, flexible sensors that track invisible light damage specific to our unique skin type,
And then communicate that directly to our sense of touch.
what other unseen chemical or physical stresses are we absorbing every single day from, I don't know, micropollutants, inflammation markers, environmental toxins that the next generation of smart textiles will be built to warn us about in real time?